All right. Hello, students. Welcome back to our channel. Welcome to TUTORhub, your e-classroom on YouTube. Today, we will be learning about empirical and molecular formula, and we'll learn shortcuts on how to learn this topic. So, before we start, please subscribe to the channel, like the video, and leave your comments so that we can work on more topics in the future. Are you ready now? Okay. So our first question reads, what is the empirical formula of a compound that contains 0.783 grams of carbon, 0.196 grams of hydrogen, and 0.521 grams of oxygen? So, reading the problem, we know how to, we'll be able to know how to solve this question, right? So let's break it down. So, the technique that I would usually re- tell my students, including you, is to create a table so that it would be much easier for you to determine the empirical and molecular formula of a compound. In this case, we're asked to determine the empirical formula of a compound, and we have the given masses of the compounds of the elements, the masses of the elements within the compound. So let's begin by writing the elements on the first column. So the elements in this compound are carbon, hydrogen, and oxygen, right? Carbon, hydrogen, and oxygen. In the next column, we'll write the masses of this compound. So based on of this element, so based on the given, carbon is 0.783 grams, hydrogen is 0.196 grams, and oxygen is 0.521 grams, right? But because the subscripts of the atoms within a compound are expressed as molar ratios of these elements in a compound, we need to convert the masses in grams into moles, right? So we write the molar masses of the elements. So approximately the molar mass of carbon is 12 grams per mole, hydrogen 1 gram per mole, and oxygen is 16 grams per mole. Very good. So by dividing the masses by the molar masses of the elements, we will get the mole values of each of these elements. So we divide 0.783 grams by 12 grams per mole for oxygen. And when you use your calculators, you'll be able to get 0.065 moles. Okay, right. Oops. That's 0.065 moles. Okay. Were you able to get that? Very good. And then when you divide 0.196 grams for hydrogen by 1, of course, you will get 0.196 moles. And when you divide 0.521 grams by 16 grams per mole, you'll get 0.033 moles for oxygen. Now we divide, then the next step after getting the mole values for each of these elements is to get the molar ratio, okay, of each of these elements within the compound. So to determine that is we'd like to look at the mole values that we've calculated for each of the elements and choose the lowest mole value among them. So based on this, oxygen got the lowest mole value of 0.033 moles. So we will be dividing all mole values by that. Okay, so that we'll be able to get the mole ratio of the elements in the compound. So using your calculator again, if you divide 0.065 moles by 0.033, you'll get 1.96. 0.196 divided by 0.033, you'll get 5.88. And 0.033 divided by 0.033, you get 1, right? But we can round off 1.96 to 2, 5.88 to 6, and 1 as 1. Therefore, going back to the elements, we now have this now becomes the subscripts of the elements, right? So that means our empirical formula becomes C2, because that's 2 for carbon, H6, 6 for hydrogen, and O subscript 1, we can just leave 1 as is, which corresponds for oxygen. So in our first example, the empirical formula of this compound with these masses of the elements given here would be C2H6O, right? So I hope that's clear, right? If you have any questions, please write it down in the comment section and I'll address them as soon as I can, all right? So now let's go to the next problem. Okay, we have this problem which reads, what is the empirical formula of a compound which consists of 89.14% gold and 10.80% of oxygen? So we'll follow the same process as before. So on the first column, we'll write the elements. Okay. So in this case, you only have two elements, gold and oxygen. Now, unlike in the previous example, we have in this problem the percent composition of the elements, right, within the compounds. For gold, we have 89.14% gold, and for oxygen, that's 10.80%. Now, it's safe to assume that this element, right, would total 100%, more or less 100%. Therefore, it's safe to assume that within 100% gram or 100-gram compound, we will have the masses of the elements as 89.14 grams gold and 10.80 grams of oxygen, right? So this would be the expected masses of the elements if you have a 100-gram compound. Now that we have the masses of the elements in this in this column, then we can go on with the process like in the previous problem. So what's the next step again? Very good. We need to convert the mass into moles. So we need to divide the masses using or by the molar mass of each of the elements. So for gold, the molar mass is 196.97 grams. And for oxygen, that's 16 grams. Okay. So now that's grams per mole, grams per mole. Okay. So with that, we can get the mole values of each of the elements, and dividing 89.14 by 196.97, we get 0.45, and dividing 10.80 by 16, we get 0.675. Okay. And then we get the molar ratio of each of these elements. So the process again here is to choose between the two mole values, which of these two would be the smaller value. And in this case, in this particular problem, that would be gold because it's 0.45. Therefore, to get the molar ratio, we divide both mole values by 0.45. Okay. So when we get the molar ratio, or when we divide the mole values by the molar ratio, we get 0.45 divided by 0.45. That would be 1. And 0.675 divided by 0.45, that would be 1.5. This one, the one would be corresponding to the subscript of gold, and 1.5 will be corresponding to the subscript of oxygen. So if we write that down, we have AuO 1.5. However, remember, we cannot have decimal points for our subscripts, for our elements in a molecular compound or an empirical compound. Therefore, we need to multiply the subscripts by a certain factor so that it turns into a whole number. Okay? What number do you think should we multiply to 1 and 1.5 so that we do not have any decimal places for our subscripts? Very good. If we try to multiplying 2 by 1 and 2 by 1.5, we now get AU2O3, right? So that would now be the empirical formula that we are looking for this particular problem. So in this particular problem, you notice that we needed another step, right? So that we'll arrive to the actual empirical formula of the compound, because we cannot accept or we cannot have decimal places for the subscripts of our elements in a compound. Okay, so that's why we needed to multiply our answer by 2 so that we get whole numbers for the subscripts of our empirical formula. Was that clear? If you have any questions, again, please write them down in the comment section so that I can handle them and address them for you. Okay? But before we proceed any further, don't forget to subscribe to the channel, like this video, and leave a comment so that I know how to help you better in the next videos. Okay? Now, let's go to the next problem. And this problem is similar to the previous one where we are given the percent composition of a compound, right? So we have 1, 2, 3, 4 elements this time, right? So unlike the previous one, we only have 2 elements. This time, we're solving the empirical formula of a compound with 4 elements in it. Okay. But we will not be overwhelmed because we'll be following and using the same process, all right? So still the drill is to write the elements on the first column, and our elements are nitrogen, hydrogen, sulfur, and oxygen, right? And like in the previous problem, we write the percent composition of the compounds based on the given. That's 21.2% for nitrogen, 6.1% for hydrogen, 24.2% for sulfur, and 48.5% for oxygen. Now that totals to roughly 100%. Therefore, we can assume in 100 grams compound that the masses of these elements would be 21.2 grams for nitrogen, 6.1 grams for hydrogen, 24.2 grams for sulfur, and 48.5% grams for oxygen. So approximately that would be 100 grams, right? Now, again, we need to convert this to moles. Therefore, we need to divide this by the molar masses of the elements. So remember, the molar mass of nitrogen is 14.01 grams per mole. Hydrogen is 1.01 grams per mole. Sulfur is 32 grams per mole, whereas oxygen is 16 grams per mole, right? By dividing the masses by the molar masses, we now get the mole values of each of these elements. So 21.2 divided by 14.1 will get 1.5. 6.1 divided by 1.01, we get 6.03. 24.2 grams divided by 32, we get 0.75. 48.5 grams divided by 16, we get 3.03. Again, we choose the lowest mole value among the mole values that we calculated, and that is 0.75 from sulfur. So we get the molar ratio by dividing everything by the lowest mole value, which is 0.75. That's division. All right. So by now, I think you're working on this problem faster because you've already got the pattern, right, on how to solve this particular problem. So 1.5 divided by 0.75, that would be 2. 6.03 divided by 0.75, that's 8. This would be 1, and this would be 4. So because our subscripts here, the molar ratios are whole numbers, then we can put this safely as subscripts to our elements in the compound. So that gives us N2H8SO4. So this would be the empirical formula of our compound, right? Do you find it easier now? So most likely at the start, in the first few problems, you find this particular topic really difficult, but with the process that I presented you and the table that makes this clearer, then hopefully you'll find this topic much easier at this point, right? So we're not stopping there. We'll have more example, another example. We'll have two more examples actually. And this is the fourth one, second to the last one. We're asked to determine the molecular formula of a compound with an empirical formula of CH2, and the molar mass of the compound is 180 degrees. So this is quite new compared to what we've solved a while ago because we're given the empirical formula this time, but we have the molar mass of the compound and we're asked the molecular formula. So how do we do this? How do we solve this, right? So to solve this, we get the empirical mass of the compound, of the empirical formula, of the empirical formula. So our empirical formula is CH2O, and getting the empirical mass would involve adding the molar masses of the elements within the empirical formula. So in this case, to calculate the empirical mass, that's carbon, hydrogen, and oxygen, the molar mass of carbon is approximately 12 grams per mole, hydrogen is 1 gram per mole, and oxygen is 16 grams per mole. And we only have one carbon atom, we have two hydrogen atoms, and one oxygen atom. So simplifying that further, you have 12, 2, and 16. Adding everything up, you have 0, 3, right? That's 30 grams per mole as the empirical formula. Now, why did we solve that? We need to determine the relationship between the empirical mass and the molecular mass. Okay, I think this should be molecular mass. Okay, the molar mass, yeah. Stand corrected. The molar mass or the mass of the actual molecule, right? So we're given 180 grams per mole. That's the actual molar mass of the compound. So we need to get the relationship between this so that we know what factor to multiply to our empirical formula. So in this case, that would be 180 grams per mole divided by 30 grams per mole. So if we divide these two values, we'll get 6 as the answer, right? That means that we need to multiply our empirical formula by 6 so that we'll get the actual molecular formula of the compound. So in that case, CH2O, if we multiply that by 6, we'll get C6H12O, 6, right? So that's a similar molecular formula as glucose. So that would be the answer to this problem. So you see, this is much different to what we had in the previous three problems because we're given the empirical mass, we're given the molar mass of the molecular compound, and then we solve the empirical mass of the empirical formula, related that with the molar mass of the molecular compound. We got a factor and multiply that factor to the empirical formula so that we'll get the final molecular formula that we are required to determine. All right? So I hope that's clear. If you have any questions, again, leave it in the comment section and I'll address it as soon as we can. And for this session, we now have our final question, right? So we have a sample weighing 3.535 grams, which contains uh, 1.388 grams of carbon, 0.3845 grams of hydrogen, 1.850 grams of oxygen, with a molar mass of 62. So you're asked to determine the molecular formula of the substance, right? So how do we solve this? Okay, so to solve this, we need to first determine the percent composition of our elements, right? Because it's not 100%, how do you call that? 100% compound, then we can use, or we can first determine the the percent composition of each of the elements in the compound, right? So we first write the table. For the first column, we have the elements, right? So you have carbon, hydrogen, and oxygen. So we have the masses of the compounds. Okay, that's carbon 1.388 grams, hydrogen 0.345 grams, oxygen 1.850 grams. Okay, so the total mass is, does it total to 3.585? Let's check. Get your calculators. 1.388 plus 0.345 plus 1.850. So that's equal to 3.583. Okay. Now, we first convert, we first determine the percent composition of each of the elements. So we divide all these masses by the total mass of the compound, right? So if you have 1.388 grams divided by 3.585, that would be 38.7%. For hydrogen, that would be 9.62%. And for oxygen, that's 51.6%, right? Okay. So again, we determine the percent composition by dividing mass over total mass of sample. Okay, that's mass of element over mass of the sample. Okay, that's how we determined the percent composition. So this is more or less 100% compound. So because it's 100%, we can assume that the mass of the compound in a 100-gram compound would be, of the elements in a 100-gram compound would be 38.7 grams. This would be 9.62 grams and 51.6 grams. So more or less that would be 100 grams. So we already have the mass. Then we do the drill like before. So that would be converting this to moles. So we divide that by the molar masses of the elements. So the molar mass of carbon is 12 grams per mole, hydrogen is 1 gram per mole, and oxygen is 16 grams per mole. So now that we have the molar masses, we get the moles first, the mole values. 38.7 divided by 12, you get 3.22. This 9.62 divided by 1, you have 9.62. 51.6 divided by 16, you get 3.22 moles, right? Then we get the molar ratio. So by looking at the mole values, 3.22 is the lowest mole value among the mole values that we calculated. So we divide everything by 3.22, right? So we get our mole ratio as, for a carbon, that would be 1. For hydrogen, that would be 3. And for oxygen, that would be 1 as well, right? So that gives us the formula CH3O, right? However, remember, we're given the molar mass of the compound, right? Of the empirical formula. So again, this is a combination of the first three problems that we had and the fourth problem or the previous problem that we calculated. So we have the molar mass of the actual compound and we relate it with the empirical mass of this compound, of the empirical mass of this formula, right? So we have, first we calculate the empirical mass. That would be carbon, hydrogen, oxygen. Carbon is 12, hydrogen is 1, oxygen 16, but we only have one carbon, 3 hydrogens times 3 times 1, that would be 31 grams per mole. Relate that with 62 grams, which is the molar mass of the compound. So N, or the factor that we need to multiply to the empirical formula, would be 62 grams per mole divided by 31 grams per mole. So dividing that, N equals 2. Very good, right? So 2 would be the factor that we multiply to our, to our empirical formula. So that would be CH3O times 2. So we get, our final answer would be C2H6O2. So this would now be the molecular formula of the compound. All right, so this last problem is a bit of a combination of the previous simple calculations that we had and relating empirical mass with the molecular mass and the molecular formula of our actual compound. Okay, so I hope you learned something today. And if you have any questions, don't forget to subscribe to this channel so that you'll be updated about our next topics. Like this video and leave a comment so that I'll be able to interact with you and we'll learn more in our next videos. So again, thank you students for learning with me. Until next time, see you in our next video and happy learning everyone. Thank you.